So in this video we're going to go through the proof of de Moivre's theorem by induction. So first of all we're just going to make a note of de Moivre's theorem. So the theorem tells us that if we have cosine theta plus I sine theta to the power of n, that this is equal to cosine n theta plus I sine n theta. And this is for all real values of n. So this is what we're trying to prove. So proof by induction, we have three different steps. Step 1, we let n be equal to 1. Step 2, we assume that it's true for n is equal to k. And step 3, we prove that it's true for n is equal to k plus 1. And by doing this, we prove that it's true for all real values of n. So back to step 1, we let n be equal to 1. So we take cosine theta plus I sine theta, all of that to the power of 1. We know this is equal to cosine theta plus I sine theta. On to number 2, we assume that it's true when n is equal to k. So we assume cosine theta plus I sine theta to the power of k is equal to cosine k theta plus I sine k theta. So step 3, we prove true for n is equal to k plus 1. So what we want to show is that cosine theta plus I sine theta to the power of k plus 1 is equal to cosine k plus 1 theta plus I sine k plus 1 theta. So now we're really getting into the kind of formal proof of the question. So I'm going to go through this with as much kind of extra explanation as possible, and hopefully it won't overcomplicate things. So the first thing that we're going to look at is cosine theta plus I sine theta to the power of k plus 1. So we need page 21 of the log tables to find the laws of indices. The very first rule tells us that if we have a to the power of x plus y, that's equal to a to the power of x multiplied by a to the power of y. So it's written kind of differently in the book. That's the rule that I'm going to use to expand this, because I have k plus 1 as my power. So taking cosine theta plus I sine theta as my a, I can now break it up into cosine theta plus I sine theta to the power of k. So that's like my a to the power of x. And then that's multiplied by cosine theta plus I sine theta to the power of 1. So this is the law that I'm talking about, or the rule that I'm using. So we've assumed from part 2 that cosine theta plus I sine theta to the power of k is equal to cosine k theta plus I sine k theta. And then if it's to the power of 1, we just have cosine theta plus I sine theta. So now I multiply out my brackets. So the first term in the first bracket by the first term in the second bracket, cosine k theta by cosine theta. First term by second term, so it's plus cosine k theta by I sine theta. Second term by first term in the second bracket, I sine k theta by cosine theta. And then the second term by the second term, we get I sine k theta. I'll just have to write it down here, by I sine theta. So really in that last term, when I have I sine k theta multiplied by I sine theta, really that's just going to be I squared sine k theta. So to save me just writing that all out again, we know that any time I have I squared, really that changes to minus 1. So therefore that final term is going to be minus sine k theta sine theta. So I'm going to put together the terms that are real and the terms that are imaginary. So my first term is real, second one is imaginary, third one is imaginary, and then my fourth one is real. So cosine k theta by cosine theta minus sine k theta sine theta, and then plus cosine k theta I sine theta plus I sine k theta cosine theta. Now you could take a few shortcuts with this, but I just want to take it really step by step so that you can see exactly what I'm doing. Okay, so next line, all I'm going to do is take out the I from the two imaginary terms. Again, really you could have done this in the last step. So I have I cosine k theta sine theta plus sine k theta cosine theta. So again, for this next bit, I'm just going to pause for a second and identify the rule that I'm going to use for the next step. So on page 14 of the log tables, we have our compound angle formulae. So this is kind of our trigonometry section. The very first rule on the page tells me that if I have cosine A plus B, that's equal to cosine A, cosine B, minus sine A, sine B. So if we take k theta as A and theta as B, so again, this will be our A, this would be our B. What we have is cosine A, cosine B, minus sine A, sine B. So therefore, we can simplify what we have, and it's really going to give us cosine k theta plus theta. So that's what I'm going to do now. So this will simplify to be cosine k theta plus theta. So using the next rule on that page, I'm going to do the same for cosine k theta sine theta plus sine k theta cosine theta. That rule tells me that this will simplify to give me I sine k theta plus theta. So if we scroll up, we see that we want it in the form of k plus 1 theta. So what we're going to do now is factorize, just take the q on the outside of the bracket. So we will have cosine k plus 1 theta plus I sine k plus 1 theta. So now all we have to do is sum up at the end. So therefore, if it's true for n is equal to k, which we assumed, then it's true for n is equal to k plus 1, but it's true for n is equal to 1, so it's true for n is equal to 1 plus 1, which is equal to 2. So therefore, the theorem is true for n is equal to 1, 2, 3, continuing to infinity, so for all positive integers. And that's the proof of the Moivre theorem done.